So everyone can hear me, I hope? Good. Yeah, so my name is Mike Reiter. I'm going to be talking about some work done by one of my graduate students, Shoyu, who's the first author. He should be here presenting this, but he took an internship outside the country, couldn't get the time to come back, left me to come and present. So apologies for that, you're kind of stuck with me. It's also joint work with Inshin Zhang, one of my former students who's now a professor at Ohio State. I guess it won't come as a surprise to folks in this room that TLS does a great job of protecting payload security, but it doesn't maybe do a great job of protecting the privacy of the users, or users' privacy when they're accessing different servers. The reason for that really arises from a variety of fields that get transmitted in the clear over the network. For example, in DNS queries, your domain name that you're querying gets exposed. When you set up the TLS session, there's an SNI field that exposes the domain name. The certificate subject name has a domain name. There is a public key that can stand as a long-term identifier for the server as well. Then, of course, there's the IP address that gets disclosed too. So really, the server you're contacting is pretty much out there, okay, even though you're using TLS. And also, it won't come as a surprise to folks in this crowd that can become an issue, right? For sometimes when that information is disclosed, then the privacy ramifications that result can have significant consequences. And so this is the problem we're trying to address. We would like to implement server anonymity for users so that when they access servers, it's not clear to a network observer who it is they're accessing or what server it is they're accessing. Now, there are a number of approaches you might take to deal with this problem. One of them is to just basically use VPN tunneling, right? Tunnel your request out to a VPN endpoint where it exits and then goes off to the server. This can help in some respects. I'll return to this topic later. This is not what we do. The other thing, of course, you can do is use an anonymizing network, perhaps Tor, obviously the most widely used one. This actually does more than what I'm asking, right? It protects server identity, but can also provide some other interesting properties and useful properties too. One thing we've seen emerge in this space in the last several years is the use of clouds and CDNs as a tool for providing a degree of anonymity. And there have been a number of example solutions like this. I've just put a few of them up on the slide. A couple of these do things better than what we're going to do today in one sense, which is, for example, things like cloud transport and domain fronting leverage these infrastructures without assuming their cooperation. They just simply assume they're oblivious. They don't work against you, but they don't work for you. The perspective we're going to take in this talk is to ask the question, if the cloud provider was willing to help clients access their tenant servers privately, what would it do? How would it best do it? So we're going to leverage the cloud as a partner here in this work. Another example in this space is something like Cache Browser, which is actually designed for a somewhat different threat model. So, for example, for our purposes, it isn't ideal because it leaves the domain name visible in the TLS SNI field. But again, it's really targeted at a different kind of problem than we're targeting here. But I just want to put it up as an example of another work that's used clouds or CDNs as a sort of a backbone for providing privacy properties. So we're going to do the same thing. Basically our solution, right, is something we call personalized pseudonyms for a server in the cloud, which somewhat astonishingly turns into an acronym, Popsicle. It's not the frozen treat, right, that you have after you've had a meal, but it's a pseudonym for a server. And the server has to be running in the cloud in the sense that the anonymity set for the server is going to be the set of all of the tenant servers running in the same data center in the cloud. So if you're the only one running there, then yeah, your anonymity set's no good. But if you have lots of servers running in that data center, then you get the benefits of some privacy. And so what we're going to do is we're going to replace all of these domain names and things with pseudonyms, right? So there's going to be some pseudonym for the domain name that gets populated everywhere in this picture. There's going to be a new public key. There's going to be a different IP address that's not related to the tenant server that's being accessed. And so all these identifiers go away from the adversary's point of view. And now, one of the things we gain by trusting and having the cloud work with us as a partner is that we can end up doing this without making any client software changes, which is really neat. So you can use this with your standard browsers. You don't have to install anything. And we wanted to do that for two reasons, right? One is that we wanted to enable users who may not have the permissions to install new software on their computers. Like if you're using a company computer and you wanted to nevertheless get a pseudonym that you can use for a server, maybe you don't have the permissions to update the software there, and so you have to work with what you have. The other thing is there's just good reasons maybe you don't want to install new software, right? There's been a long-running history of even security software like malware, and antivirus and so forth, opening up all kinds of holes. So maybe you're really not interested in the next new cool research piece of technology that you'd like to put on your computer because it probably is going to cause you to get compromised in other ways. We also don't sort of have a proxy sitting out there in the cloud. I'll return again to this later, but from a performance point of view, proxy isn't that great, and we'll talk about that. Okay, so let's talk about our threat model just briefly. So what is, in the context of a particular client-server connection, what is trusted? Well, we're trusting the client computer and we're trusting the cloud infrastructure. So again, the cloud is trusted, it already is trusted in most of our interactions with tenant servers, of course, but we're going to trust it and it's even going to cooperate with us in certain ways. What isn't trusted is the network between the client and the cloud. So that can be observed and manipulated and such. And other clients and other servers. So we don't trust other tenant servers, we don't trust other clients. What this looks like from the user's point of view is something like this. There's actually a video on my students' webpage if you want to go look at the video of how of him exercising the system. But at a very high level, what it looks like is you go to something that we call the popsicle store, and you say, hey, look, I would like a pseudonym for www.example.com. And what comes back to the user is a pseudonym, right? This big, ugly FF5 blah, blah, blah thing. It has a question mark capability equals after that. I don't think in this talk I'm going to have to be able to describe you why that capability is there, but it's needed. It's in the paper. We'll talk, so check it out. But the other thing that you'll notice is that you're given, the user is given a client cert and private key. So this uses client-side TLS. You have to install this. Fortunately, all major browsers support this anyway, and there's at least existence proofs of substantial deployments where people have gotten along with this just fine. We're going to leverage this here. The reason we're using it is to make sure that I can use my popsicle to access a server, but nobody else can. Because if somebody else can access the server using my popsicle, they can, of course, figure out what it's returning and then de-anonymize what it is. So you're going to need this client cert to use the popsicle in a TLS connection. Okay. So now how does this work under the covers? So here we have a client on the left, and we have a bunch of other boxes, which are all part of the cloud and such on the right. The user is going to go to that popsicle store and say, hey, I would like a popsicle. And so what's going to happen is a few things. The popsicle store is first off going to create the popsicle, as well as a pseudonymous IP address, which is actually the IP address of an SDN controller that's running in the same data center as the tenant server. And this is, so basically for all the tenant servers in that data center, they're going to get a pseudonymous IP that's really just an SDN controller of the data center. In addition, right, so first of all, that will be provided to the DNS infrastructure for resolving the popsicle. Secondly, the popsicle store is going to create a mapping between the popsicle and the real identification of the tenant server that will be made accessible to the SDN controller, because when that SDN controller starts getting traffic for this popsicle, it needs to know where it really needs to go. Thirdly, the popsicle store is going to create the client cert for the client, as well as a server-side cert, a new cert, for use in TLS connections with this popsicle. It'll sign the server cert with the cloud's private key, so that needs to be a trusted CA for the user. And then the server cert, for all our purposes right now, is just used to sign the client cert. And this then is distributed where you think it might be, which is you take the server-side stuff and you give it to the tenant server, and you take the client-side stuff and you give it to the client. And that's the setup. Okay, now, later, when the client comes along, and the client can only bookmark this and use it, you know, arbitrarily in the future. When the client comes along later and says, hey, I'd like to connect to that thing, it does a DNS lookup, gets back, on the popsicle, of course, gets back the pseudonymous IP, which again is an IP address of the SDN controller in the data center. A connection is made to the SDN controller. Now what that means is that when the traffic hits the switch in the data center, it's just going to be routed to the controller. So it gets routed to the controller. The controller goes ahead and completes the TCP connection with the client and awaits the client hello message of the TLS connection. And when it sees that, it now knows what popsicle the client wants to access, and it can look up what the real tenant is. And so it says, okay, well, what I'm now going to do is I'm going to first install some temporary rules in the SDN switch to do two things, right? The first one is it will block, just for the moment, it will block new inbound traffic from the client. You'll see why in just a second. And it will set up another rule that says responses will get, the source address will be mapped to come from the pseudonymous IP. So when anybody responds out of the cloud, right, the bad guy on the outside who's watching all this doesn't get to see what the real IP address of the tenant server is. Now, the reason that the inbound traffic from the client is blocked is to put a hold on inbound stuff, because what we're going to do now is the SDN controller actually migrates the TCP state to the real tenant server. So we're going to take the TCP state, move machines to the tenant server so it can pick up where the controller left off. And then, right, the controller will update that first rule that was dropping new inbound traffic from that client to the server to simply say, okay, let it go now. We're going to remap anything coming in for the SDN controller from that particular client server port to the tenant server that it was trying to access. Then, right, the client can start connecting and talking to the server, just picking up where the controller left off. The one last piece of this is that this tenant server has to decline this whole everything, right, shut it all down if the client doesn't demonstrate possession of the private key. So if it's really not the right client, then the tenant server has to cut off everything, all right, and just not return any content. And that's what that's where sort of the guarantee that only I can use my popsicle comes into play. So yeah, I know that's a really ugly slide now that everything's up on it. My apologies. So in the interest of time, there's a number of HTTP-specific mechanisms that you have to incorporate into this to use it for web traffic. One of them is an object linker, because if a tenant A is going to hyperlink to tenant B, you don't want tenant A needing to know what popsicle I use for tenant B. And so if you want to enable it to link by hyperlink by popsicle, you have to provide some level of indirection in here, and so we call that in the paper the linker. So you can kind of connect through the linker, or sorry, hyperlink through the linker, and the linker does a redirection effectively to the right popsicle if it's permitted, if tenant B in this case is permitted tenant A to hyperlink to it in this way. But again, that's just sort of some HTTP specific stuff. There's some other stuff in the paper, how to deal with cross-site request forgeries. Just a hint, that's where that capability comes from that I'm not going to tell you any more about. There's also some stuff in the paper about dealing with traffic analysis. Again, I'm not going to touch that. What I did want to do is talk briefly about the scalability of the solution, because we are introducing per client server state into lots of places in the cloud infrastructure. 1 minute, okay. Let's see. So let me just sort of run through a bunch of graphs really fast, and the punchline is it scales pretty well. So first of all, let's talk about latency. This is the connection latency of HTTPS in our setup. We were going to a cloud, to the Cloud Lab cloud, where we had set up servers to do this. Here's what our latency looks like, and because everyone compares to Tor, we'll compare to Tor 2. For the same reasons Roger said after the last talk, it isn't entirely fair. It's also not fair because Tor does more than what we do, but everyone compares to Tor, so there's our comparison to Tor. So in terms of throughput, we suffer a little worse. So latency does cost. We suffer very little in latency, but for throughput, we suffer a little bit more. Here's HTTPS, client-side HTTPS, and then us. And so what you see here is, what you see here is that we do have a 30% degradation in throughput ballpark. Now, again, let's talk about scalability. We tried to test scalability of this design on a number of different axes. So one of them was if you throw a lot of connections at the system, you're potentially overloading your SDN controller. What happens? This is basically what happens. So this is if you were just doing regular HTTPS connections in our setup, you get the red line. With popsicles and all those TCP handoffs, you're getting the green line. So it's not horrible, but you are costing yourself something. We also wanted to look at performance as a function of the volume of stuff you're retrieving. And we did this primarily to highlight the distinction between a proxy-based solution and what we do. See, a proxy-based solution is going to decay dramatically in terms of the number of responses per second as the size of those responses increases because it's handling all the bytes. Whereas because we hand off the TCP connections, it doesn't impact us at all. And so from a scalability point of view on this front, we win big. Of course, if you have a scenario where all of your objects are tiny, the TCP handoff ends up costing you more. I know, 30 seconds, I'll get there. So another thing we do is we had a lot of switch rules into the SDN switches. What does that mean for our performance? Here are two graphs for different web object retrieval sizes, but Open vSwitch has this interesting plateau phenomenon going on where even as you add large number of rules, it kind of has this one knee in the curve where it jumps into a different method for handling the rules. But it really stays quite stable as you grow the number of rules in the switch. So from a scaling point of view on that front, things look pretty good too. As you add new popsicles to a server, these get realized in our implementation as virtual hosts in an Nginx sense. So this is a new data structure on the server. What happens is you add lots and lots of users, that is lots and lots of popsicles on a single server. It turns out the answer is nothing for Nginx. So this is say the latency for retrieving 10 kilobyte messages, right, from a server. Here's, for a different object size, but the bottom line is the number of virtual hosts really doesn't have a huge impact in your setup cost to be able to do this. So from most of the angles that we've been able to see, this really isn't a scalability problem, even though we are making a lot more state in the network. Okay. With that, I will stop and answer any questions you have. Apologies for going over.